Hello, I am Saranga Bandara from the Open University of Sri Lanka. In this short video, I am going to talk about Maxwell's equations. The history of Maxwell's equations dates back to the 19th century. Faraday, Ampere, and Gauss laid the foundation of electromagnetism. Maxwell unified these laws into a single theory in 1864. These equations describe how electric and magnetic fields interact and propagate as waves. This formulation led to the discovery that light is an electromagnetic wave. Physical meaning of Maxwell's equations. The first law is Gauss' law for electric field. It says that the electric charge produces electric flux. The second law is Gauss' law for magnetism, and it denotes that no magnetic monopoles exist. Faraday's law is the third law, and it says that changing magnetic fields induce electric fields. Finally, Ampere-Maxwell law describes the currents, and changing electric fields generate magnetic fields. Each of the four equations has differential and integral forms as shown in the table. Gauss' law for electric fields. Electric flux through a closed surface equals the charge enclosed by the surface, divided by the permittivity of the medium. It illustrates that the electric field lines originate from charges. This law is useful for solving problems with high symmetry, spherical, cylindrical, or planar. Gauss' law for magnetism. The magnetic field lines always form closed loops. The law implies that magnetic monopoles do not exist. Total magnetic flux through any closed surface is zero. And finally, this indicates the symmetry between electric and magnetic fields. Faraday's law of induction. A time-varying magnetic field induces an electromotive force. We simply called it EMF. The equation expresses electromagnetic induction. This equation is used to explain the operation of generators and transformers. Lenz's law ensures that the induced EMF opposes the change in flux. Ampere-Maxwell law. Ampere's original law applies to steady currents. But later, Maxwell introduced the displacement current term into the equation. This modification enables us to explain the continuity of current in capacitors and time-varying fields. Furthermore, it unifies electricity and magnetism under time-varying conditions. Electromagnetic wave equation. Combining Faraday's law and Ampere-Maxwell law gives the wave equation. Then we can determine the wave speed 3 times 10 m(s), which is equal to the speed of light. This further proves that light is an electromagnetic wave. Now we will see some of the applications of Maxwell's equations in different areas. Transmission lines and antennas. Waveguides and optical fibers. Wireless communication and radar systems. MRI, inductive charging, and electromagnetic sensors. Foundation for modern electromagnetics and photonics. Now I'll present you with some discussion questions. You can research and find the theoretical background of them. First, what is the role of the displacement current in Ampere's law? Why can't magnetic monopoles exist? How do Maxwell's equations lead to electromagnetic waves? How are these principles applied in modern communication systems? That is all for this video, and we will meet in another one soon. Thank you.